Hello class. So on this video, we'll finally explain what does it mean for a vector to be a solution to a system of first order linear equations. Okay? So what a solution is what it was in the previous case, which is just a set of functions that satisfy the differential equations. Right? So here I just wrote them as 2 or 3. So let's go back to our system. Right? So a solution to either equation 2 or equation 3 is a vector x that when you plug it in, meaning that you multiply a times x, and you calculate the derivatives of each entry in x. Right? When you do all that, whatever's on the left of this equation has to be equal to whatever's on the right. Right? So very similar to what it means for a function to be a solution for a single differential equation. In this case, we're asking when is a vector a solution to a system of linear equations. Is that that's what it means? Given a vector x, find the matrix product AX, find its derivative, and whatever's on the left has to be equal to whatever's on the right. In both cases. Right? In the case of system 2, you're also going to have to add, but we already saw how to add. Right? In the case 3, where you have a homogeneous system, you don't have to add anything. So it's as simple as that. So let's see an example. Okay. So verify that x1 equal to e to the negative 2t, that's the first entry, and negative e to the negative 2t, and x2 equal to 3 times e to the 6t, that's the first entry, and 5 times e to the 6t are solutions to this system on negative infinity to infinity. So again, anytime we talk about solutions, we have to talk about its interval of definition. But the conditions are basically the same as before. Are the functions defined? Is there anything in the equations that are going to restrict the values that t can attain? Right? But if nothing of that is a problem, then it's just going to be negative infinity to infinity. If, for example, one of these functions were square root of t, then our t would have to be greater than or equal to 0. So basically, you check the same things that you check in the case that you have just one differential equation. So it's the same thing in terms of the interval of definition. Okay? So we need to verify that both of these are solutions. So the first thing we're going to do is we're going to write our system or using matrices. Okay? So our x prime is going to be, or let's just start with our x. So x is the vector containing the variables. In this case, we have variables x1 and x2. Actually, since we're only using 2, let me change them to x and y. Again, it's just easier to visualize it in that manner. So let me write x, y, x, y. Okay. So our variables are x and y, the dependent variables. The matrix is, again, just read off the coefficients. And again, notice that I write x entries first, y entries second. Okay? So first row, there's a 1 in front of the x and a 3 in front of the y. Second row, there's a 5 in front of the x and a 3 in front of the y. Then they're homogeneous, right? There's no terms that are not being multiplied by derivatives of the dependent variables. And so the last thing left to define is the matrix of derivatives. So x prime, y prime. So we can write this system in a more shorthand manner as x prime equals a 1, 3, 5, 3 times x, which is x prime, xy. So actually, let me do it like this. So x prime equals ax, which is the same as saying, right, which is the same as saying x1, I keep going back to x1, x prime, y prime equals 1, 3, 5, 3 x. Now, once you have your system like this, what are you going to do? You have to verify that both of these are solutions. So we're just going to plug them in for our variables. Okay? So working with x1, so for x1 equal to e to the negative 2t, negative e to the negative 2t, How do we plug this in? Well, this is telling us what our x and y are. Okay. So let's plug everything in. So for the first part, we need to find the derivatives of both of these functions, right? So what's the derivative of e to the negative 2t? That is going to be equal to negative 2 e to the negative 2t. That's a derivative of x. What's the derivative of y? Well, y is equal to negative e to the negative 2t. So the derivative is 2 e to the negative 2t by the chain. It's equal to 1353 times xy. Again, x is e to the negative 2t times negative e to the negative 2t. Now, we simplify the right-hand side by doing matrix multiplication, and whatever we get on the left-hand side has to be equal to whatever we have on the right-hand side. So let's see if it's the case. So let's do this matrix vector multiplication. So working row by row, the first entry is going to be, okay, the first entry in row 1 times the first entry in the vector, that's 1 times e to the negative 2t, plus the first entry in row 1 times the second entry in the vector, that's 3 times negative e to the negative 2t, and that's the first entry in the vector, resulting vector. Now go to the second row. First entry in the second row times the first entry in the vector, that's going to be 5 times e to the negative 2t. Then go to the second entry in the second row, which is 3, and multiply it by the second entry in the vector, which is negative e to the negative 2t. Simplify this, what do we get? We get 1 minus 3 is minus 2. And then on the bottom we get 5 plus minus 3. So we get positive 2. And you can see that we get equality. Right, so this, which is the right-hand side, equals the left-hand side. So let me do what implies there. How do you tell if two matrices are equal? Just check each of their corresponding entries have to be equal. Right, so the first entry here, negative 2 e to the negative 2t, okay, matches the first entry in the left-hand side. Okay, the second entry in the right-hand side, 2 e to the negative 2t, matches the second entry in the left side. Okay? And that's how you verify whether a vector is a solution to this system. Okay? Now, for extra practice, let's do the other solution as well. Okay? So the left-hand side, so we already set up what the system looks like. We only have to plug in the vector. So in this case, the vector is given by x equals, this is x2, so x2 equals 3, 5. Okay, so I just look at the coefficients and remember the rest. So 3 e to the 60, 5 e to the 60. Okay? Again, we want to plug this into the system that we wrote above. I'm just going to write it here again. X prime equals ax. So let's calculate the things that we have to calculate. Okay. So a was already calculated. We have to find what x prime is. So let's just take the derivatives of each entry. So derivative of the first entry is, so a 6 down by the chain rule, so 18 e to the 60. For the second entry, again by the chain rule, bring the 6 down, 30 e to the 60. Now, let's plug everything into this equation, and we must get equality. So the left-hand side is this that we found, right? 18 e to the 60, 30 e to the 60. The right-hand side is given by a, which is 1353. So 1353 times just the vector x, which is just 3 e to the 60, 5 e to the 60. So let's calculate this matrix multiplication on the right-hand side, and we should get equality with what is on the left-hand side. So let's verify. Okay. So again, working row by row to calculate the matrix multiplication. First entry in the first row times the first entry in the vector, that's 1 times 3 e to the 6t, plus second entry in the first row times second entry in the vector, that's 3 times 5 e to the 6t. Okay. Now go to the second row. First entry in the second row times first entry in the vector, that is 5 times 3 e to the 6t, plus second entry in the second row times second entry in the vector, that's 3 times 5 times e to the 6t. Right. Now let's simplify. So let's simplify the addition. So we have 3 e to the 6t plus 15 e to the 6t, that's 18 of them. On the bottom we have 15 e to the 6t plus 15 e to the 6t, that's 30 of them. And we see we get equality. This matrix multiplication is equal to what we had on the left-hand side. So both x1 and x2 are solutions to this ODE. And it's as simple as that. So just as in the case of just having one ODE, one equation, it was very easy to verify whether a function is a solution. Just plug it in and see if you get equality. It's as easy for systems of linear equations. Just plug everything into the equation that we have with matrices, and then after you simplify, whatever's on the left has to be equal to whatever's on the right. So verifying if vectors are solutions is very easy.